Okay, folks, let's start talking about something called the fundamental theorem of algebra. Okay, something with a name like fundamental theorem is pretty important, as you can imagine here. Let's go ahead and talk about it here. A non-constant complex polynomial of degree n has exactly n zeros in the complex numbers if we count multiplicity. Okay? Now, when I say a complex polynomial, remember that includes what? Real polynomials, rational polynomials, integer polynomials. Those are all complex numbers too. Okay? So this pretty much covers everything, right? Okay? N zeros counting multiplicity. So we've seen situations like this where we might have zeros of a polynomial that we count multiple times. Okay? In order for this to work out where the degree is exactly equal to the number of zeros, you may need to go actually to the complex numbers, with a non-zero imaginary part. Sometimes you don't. Okay, sometimes the complex numbers we talk about here being zeros might actually be real. And you might have to count multiplicity here for this to work out. But if you do, it'll always work out. The degree and the number of zeros will be equal here. Okay, it has to be a non-constant polynomial for this to work, though. Okay, here's another form of the fundamental theorem of algebra. Okay, this is going to be very important. In fact, we're going to be using it a lot this way. Okay, if I have a polynomial p of x written this way, so here I'm imagining the degree is n is greater than or equal to 1, so it's not a constant polynomial. There exist n complex numbers, okay, z for zeros, okay, n complex numbers, not necessarily distinct, okay, not necessarily distinct, such that these are what actually zeros of the polynomial, each of these, and our polynomial can be factored this way. The leading coefficient there in front might have to be there, have to be there to get the p of x, okay, often that's just a 1 there, so we could drop it. But then what? We get all these other monic linear factors, x minus z1, x minus z2, so on and so forth, down to x minus z sub n. It's saying the what? P of x actually factors in terms of its zeros, okay? So the complex polynomial will factor in terms of its zeros. And remember, a complex polynomial may include real polynomials, right? You don't need imaginary parts, okay? In fact, I'm going to do that right now. Let's consider this polynomial. P of x is x cubed minus 1. Okay, you can see that's degree 3. That's a third degree polynomial. The leading coefficient we would call, if we're using this formalism here, a sub 3, and that's going to be 1, right? This is a monic polynomial, so it's just implicit, the leading coefficient here. Now I ask you to find all the zeros of the polynomial p of x. How many should there be? There should be a total of 3 if we're going to count multiplicity and everything. Okay, now let's see. Let's go ahead and imagine setting this equal to 0. Okay, and we want to think if we can see any solution right off the bat. I can think of one. X equals 0 satisfies this. X equals 1 would imply that what? 1 cubed minus 1 is 0. So x equals 1, or let's just write it this way, maybe 1 is a 0 of p of x, our polynomial. Now you remember from the factor theorem, if 1 is a 0 of the polynomial, that means x minus 1 must be what? A factor, is a factor of p of x. So let's go ahead and imagine using maybe synthetic division. Hey, that would be perfect on this, right? Let's say I took my polynomial p of x and divided it by x minus 1. Let's just do that. Now you remember my x minus a is what we were calling the x minus 1. That implies a equals 1. Yes, that's my 0 here. Okay, so my 0 goes right up there, performing this synthetic division. Okay, my p of x, remember, you have to include missing terms. That's 1x cubed, 0x squared, 0x, and minus 1. Now remember down here at the end, I would get the remainder. That remainder better be what? 0, if I do everything right. Okay, let's bring down the 1. Okay, multiply, we get what? 1 times 1 is 1. Add, remember in synthetic division we add. 1 times 1 is 1. Add, 1 times 1 is 1. Add, we get 0. Indeed, this should be the polynomial evaluated at 1. Do you remember what this stuff was? These were the coefficients of q of x. Now, q of x is going to have a degree 1 less than p because I'm dividing by a first degree polynomial. So that's really 1x squared, which is x squared, plus 1x, which is x plus 1. And that's our quotient here. Okay? So what have we really shown? We've shown that p of x is quotient x squared plus x plus 1 times x minus 1 plus remainder 0, right? So we can skip that, okay? All right, so we've actually got a factorization of our original polynomial, p of x. I guess I can write this here now, okay, if I want to. Alrighty. Now, remember, I'm trying to find zeros of this thing, right? That was our whole point here, okay? So if I imagine trying to find the zeros here, we're going to use the zero product principle here. Now, if I set this factor equal to 0, I would get x equals 1. I already know that. That's nothing new. Where do I find the remaining zeros? By taking this thing and setting it to 0 and solving. Okay. I thought we just looked at this in a previous video here. What are you going to use on this? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And we find that's actually x equals negative a half plus minus the square root of 3 times I, because that's really negative 3 underneath the square root. And you notice we have what? We've got two solutions here, right? The plus and the minus, these conjugate zeros. So here's our zeros. There are what? 1, negative 1/2 plus square root of 3 over 2i, negative 1/2 minus the square root of 3 over 2i. Okay. Now let me mention one other thing here. So this actually answers our question. But our original polynomial here factors in terms of its 0. Remember this formulation? Okay. Our polynomial will factor with what? The leading coefficient up front, and then x minus each of the zeros going through. So this is x minus 1. The leading coefficient in the x cubed was what? Or 1, so I really didn't write anything this time, but if you wanted to, you could write that factor 1 there. But anyways, x minus negative 1/2 plus the square root of 3 over 2i times x minus negative a half. Got to get the whole thing in parentheses. You're subtracting the entire 0, all right? Okay. There it is. By the way, if you were to actually multiply these out here, what would you get? Do this for exercise for you. Okay? This thing factors, that polynomial factors in terms of its zeros. The leading coefficient there is 1 also. You actually multiply these together, you get that. Okay? Alrighty? Okay. We'll be doing more of this. We'll go through where we figure out like one or some zeros of a polynomial and find the remaining zeros. Okay? Alrighty. Okay, next let's talk about something else that's not too difficult here. This is something called the rational zeros theorem. Okay? Suppose that f of x, I'm not calling it p of x this time for a certain reason. I'll show you here in a second why. Let f of x be a sub n, x to the n, a sub n minus 1, x to the n minus 1, so forth all the way down. Be an integer polynomial. Okay, so all these coefficients are integers, right? Okay, the other little stipulation, I'm assuming the leading coefficient and actually the constant term here at the end are non-zero. They're all integers, but the additional condition is the first and last coefficients are non-zero. Now, here's the statement of the theorem then. If P over Q is a rational zero, right, that means a ratio of integers. If P over Q is a rational zero of f of x in lowest terms, so that means the only common factor between P and Q is what? plus or minus 1, then what has to happen is that the p, the numerator in the rational zero, has to divide the constant term, and the q has to divide the leading coefficient. Okay? Now, I'll show you the types of questions that we will be using these on for the exam. Find all the potential rational zeros of f of x equals, let's make one up here, 3x cubed minus 4x squared plus 7x minus 2. Okay? This is going to be a very easy question here. Now, I'm just going to say the integer factors. Later on, I'll probably just say factors, understanding they're integers. But here's what you want to do. The first thing you want to do when you see a problem like this is list the integer factors of the constant term. Those are going to go on top, right? Remember the numerators? What? The numerator divides the constant term. Okay, so those go on top. So that's why I'm writing these first. What are the integer factors of minus 2? Well, for sure, plus 1 or minus 1. For short, I will just write plus or minus 1. Plus or minus 2 also divides negative 2. Anything else? Answer is nope, that's it. Okay, the integer factors of the leading coefficient. Leading coefficient is 3. Plus or minus 1. Remember, we're talking about integers, so you want to include the minus. Plus or minus 1, plus or minus 3. These four numbers are the only integers that divide what? That divide 3. Now, here's what you want to do. You want to get them in this order so you don't get these turned around here. When I talk about potential rational zeros, remember the numerator has to be a factor of negative 2. In this case, the denominator would have to be a factor of negative 1. So the potential or possible rational zeros, so you can write that as possible if you'd rather, potential rational zeros would be, okay, we're just going to create a list. It's these guys divided by these guys. So it's plus or minus 1 divided by plus or minus 1, plus or minus 2 on top divided by plus or minus 1. Okay. Now, we could have what? Plus or minus 1 on top, plus or minus 3 down here, plus or minus 2 divided by plus or minus 3. Now, there's no association between the pluses and minuses in any particular case here. Okay, so they're both free. This could be positive and this could be negative, independent of this being positive or negative. And that holds for each of these. So what we really have for our list is the following. Plus or minus 1 divided by plus or minus 1. The ultimate result is either positive or negative 1. Here, the ultimate result is either positive or negative 2. Positive or negative 1/3. Positive or negative 2/3. Okay? Here's our answer. Okay? Here's what we're saying here when we talk about potential or possible rational zeros. What we're ultimately saying is, if this polynomial has any rational zeros, they must be found among this list. Okay? So if they exist, they've got to be in this list here. Okay? There's none outside of this list that could be a possible rational zero. Okay? Now, we're not saying all of them are rational zeros or even that any of them are. Okay? We're simply saying what I said before. If this polynomial has any rational zeros, it must be in this list. Okay? Okay. How many zeros does this polynomial ultimately have, by the way? 3, right? Why? Because it's degree 3. If we're allowed to possibly need to go to complex numbers and what? Including multiplicity, there's exactly 3. Well, obviously there's how many, 8 numbers listed here. They can't all be zeros. Okay? Okay, at most 3 of them could be, and maybe none of them. Okay? I hope that makes sense to you there. Let's get this focused again. I came out of focus. Anyway. Okay? Alrighty. Now, the thing to be aware of when I give you a question like this, you don't want to lose points, easy points. Remember, it's always what? On top, it's always factors of what? The constant term. And on the bottom, in the denominator, it's always what? Factors of the leading coefficient, not vice versa. A common error that students make is to do what? Get these turned around in the opposite order. So I've got the numerators where the denominators belong and so forth. Okay, so be careful about that. Okay, let's try one more, and you can stop it if you want, and just have you go ahead and list the possible rational zeros of f of x. Let's see, which one I chose. X cubed minus 3x plus 2. Okay? All right. Now what goes on top? Factors. Notice these are integer factors, so I'll just say factors this time, of 2. Plus or minus 1. Don't forget it's plus or minus 2. Factors of, what's the leading coefficient in this case? 1. So this is going to be plus or minus 1. Okay, now remember it's what? These guys divided by these guys. So the possible rational zeros would be, which would be what? Possible or potential. Okay, plus or minus 1, plus or minus 2. Okay? All right. Notice that if you're dealing with a monic polynomial, that monic integer polynomial, that the possible rational zeros would simply be a list of what? All possible integer divisors of the constant term, right? So immediately when I see this as monic, I see this is going to happen here. So I'll go plus or minus 1, plus or minus 2, bang. Okay, so not very hard here. We're going to use this theorem together with the factor theorem and stuff to talk about some problems here soon about where you're given some of the zeros of a polynomial and you want to find the remaining zeros. Okay? All right.